Welcome to the lesson 39 of industrial instrumentation. In this lesson, we will continue with the control valve. So, control valve we had started in lesson number 38. So, in the lesson 39 also we will continue. We will go in the deep details of control valves, because as I told you earlier that the control valves actually means the final control element in any industrial process. There actually whatever the measurements techniques we have seen or we have studied so far, like temperature, pressure, flow, pH, humidity, so on and so forth, you will see that ultimately is to all these things are basically these measurements are necessary to control the temperature, control the flow, control the process parameters. So, basically either you can make the heater power control, but most of the cases we will find that we have to control the flow, whether it is a gas, fluid, it does not matter. So, we will control the flow. So, by controlling the flow I can control the temperature, by controlling the flow I can control the level and so on. So, we will continue with the control valves. So, this is the control valve 2 of lesson 39. Let us look at the contents. Control valve 2 contents are types of control valves. Okay. We have seen that we have last time in 38 we have seen that we have considered they are the equal percentage valve, then quick opening, linear, but those are not the types of control valve. Those are basically the characteristics of the control valve. Flow characteristics versus the stem movement. If you vary the stem movement, how your flow characteristics varies accordingly. You can lay equal percentage, linear or quick opening, but the overall the different types of control valves are available in industry. So, we will study those in details in this particular lesson. Types of control valve, that is the contents, then control valve selection, how you select the control valve. So, this is a very important criterion, how you choose the control valve, because you will find the varieties of control valves in the process. According to need we have to select a particular control valves. Then the cavitation. Cavitation is a problem you will find in industrial process that you must prevent, we have to prevent the cavitation, otherwise the erosion of the control valve will start, and is very common in a petrochemical industries or hydrocarbon industries, where you will find that whenever there is a pressure drop, because always you will find that in this, suppose in the for an example that in a LPG plant, when the liquid petroleum gas is flowing through a pipe, so there is a mixture of the liquids and the vapor case, because now when it is passing through a control valve there is a differential pressure. So, the upstream pressure is slightly higher than the downstream pressure. Now, whenever this the liquid will flow through this one in the downstream, what will happen due to the low pressure, there is large vaporizations of the liquids into vapor, and those will start to flow in a high speed because the pressure is there. So, all these things will make the problem. We will study the details of the cavitations in the control valves. There is a formation of the bubbles, then the collapse of the bubbles, all these things will create a lot of erosions in the controller, and usually there is no way that you have to make either routine maintenance or replacements of the control valve, or by any means or the others, by some means or the other you have to stop these the cavitations, right. One of the good example you will find in the process industry, that an LPG plant you will find that suddenly a control valve starts to, what happens, you see that starts to sweating on the outside. You can see that the control valve outside is moist. You can immediately say that the cavitation has started. That means the liquid is flowing with a high velocity on the downstream. The gas is flowing, so there is a fall of temperature, that is there is a outside air is condensate outside. Your humidity is getting condensate forms, and it is depositing on the outside body of the valve. So, this is one very rough estimate or rough indications of that the cavitation has started in the control valve, right. Then we will study the control valve accessories. There are various accessories, but we will find that the valve positioner is one most important thing we must learn, because valve positioners will eliminate the hysteresis of the valve, of the stem of the valve, as well as it will make the precise control of the position, which was not there. So, that means hysteresis can be completely removed if we use a valve positioner. It is additional control excuse me, it is additional control. It is basically a proportional control. we will find it is working as a cascade control with the main control loop. So, it will make the better positions of the stem of the control valve, right. Then at the end of the lesson, the viewer will know the difference between the different types of control valves like sliding stem valves, globe valves, butterfly valves, etc., and their relative advantages and their applications. So, this we will know because these are the different types of control valves available, globe valves, butterfly valves, I mean this we will study in details, and relative advantages and disadvantages and typical applications in the process industry. How do parameters like temperature, pressure, rangeability, etc., affect the control valve selection? These obviously come in the selection of the control valves. How the temperature, pressure, all this rangeability. Rangeability means total range or the capacity. Sometimes we call capacity of the control valve, sometimes we call the rangeability. These are two same basically, affect the control valve selection. Pressure profile of a control valve, that means what is the pressure profile, how does it look, the pressure profile as you go. We have seen that in the case of orifice there is a pressure profile. Similarly, what type of pressure profile exists inside the control valve. If I proceed from the upstream, that means from inlet point to the outlet, how the pressure inside the control valve looks like, okay. That is actually we will also look at. Advantage of the valve positioners, as I told you, this is the accessories. So, what is the advantage? Valve positioner is an accessories to the control valve. Actually, it is installed fixed to the control valve itself. That means that pneumatic signal, control signal will not come directly to the control valve, it will first come to the valve positioner. Valve positioners will make some additional control signals, which will correct according to the positions, it will make some signals that will go to the diaphragm of the control valve. The diaphragm, all these things we have studied in details in the case of the lesson 38. Types of control valve. Let us look at control valve. Here means any power operated valve, whether used for continuous or on off control, right. We have control valve usually, but mostly we are talking of the pneumatic control valves, even though we are saying the control valve means any power operated valve, because I need pneumatic power to control, right. I need electric power in the case of solenoid valve. The solenoid valves usually it is on off type of valve, that we are not discussing. So, we are discussing basically control valves. We are basically discussing the pneumatic control valves. Excluding varieties such as motorized gate valves, plug valves, pinch valve, etc., control valves can be broadly classified into three main categories. What are these three main categories? Let us look at. A sliding stem valves, we have seen that the sliding stem, that means what is this? We have seen that I have a diaphragm, okay. So, this valve sits on a seat, right, is inlet, outlet, the pressure is coming and there is a spring action, there is a plug here for packing, okay, this is a packing. So, if the pressure comes, so the stem will move, this stem will move up and down and it will control the position of the seat in the position of the plug in the seat, so that thereby controlling the flow of the liquids. So, it will look like not this one, it will look like this one. Let me take a new page. So, it will look like I have a stem here. So, stem will look like this one, okay. So, liquid is flowing through this one and liquid is flowing out because there is inlet here, okay. Should erase this part. Okay. So, it will look like this. So, liquid is flowing through this one, okay. So, there is a path and liquid is flowing out through this one. So, it will look like this one, that means it is like this, liquid is flowing this, it is stopped here and it will look like this one actually. Okay. Now, what will happen, you see, that when the liquid is flowing through this one, right. So, liquid will come through this one and it will flow through these directions, right. If the valve moves upward, so there is a restriction here. So, the flow will go like this one. So, it will come like this, it will go like this one, that means it will come like this, it will flow and through this one. So, position of the stem, there is a spring here. So, position of this is already we have discussed in details in the lesson 38. So, you can see the better pictures there, because these are pictures a little complicated. So, we can see it very nicely in lesson 38. Anyway, let us come to the sliding stem valves or globe valves or angle configuration, etc. This is the these sliding stem valves, globe valves, angle configuration, etc. all comes under the sliding stem valves. Then rotary valves, these are ball and butterfly valves. Butterfly valves is used in many processes where I need a quick shut off, okay, like nuclear industries, even though butterflies has leakage, but with the Teflon coating and all this Teflon liner inside the pipe, we can make it Teflon liners on the stem itself, so we can make a tight shut off. Otherwise, I mean, butterfly valve is used because it needs action is very quick compared to the other valve, like the sliding stem valve. If you compare the sliding step line, I mean, very roughly, if you say the time constant, it is much faster. Response for the butterfly valve is much less, right? It is, I mean, it will, sorry, I mean, not less, I am saying that it's very fast. That means the time of response will be very less in this case, in the case of butterfly valve, or rotary valve. Then you have eccentric valve also. We will study all this. These are the three different categories of the control valves. Okay, sliding step valves, rotary valves, and eccentric valves. These are the three different categories of the control valve. Then sliding step valves. Let us look at the details in this. They are the most widely used control valves, as I told you. Sliding step valves. So most of the time you have seen that when you are giving examples of the control valves, we are going to the sliding stem valve. Typical sliding stem valves are globe valves, angle, and Y pattern. These are the three different patterns we will see. We will see the sliding globe, angle, and Y pattern. These are available in various sizes and various designs. Okay, very widely used control valves. Then ruggedness, dependability, precise throttling capabilities. Throttling means, I mean, precise passing of the liquid. That means if I say that the for this particular position, this much of liquid will flow, or this much of liquid will flow, this will be the volumetric flow of the liquid, that can be precisely achieved in the case of this type of valve, sliding stem valve. High overall performance and general sturdiness are some of the qualities of the sliding stem valves. It is very rugged, very sturdy, so okay, so it is widely used in the industry. They are more suitable for extreme applications which involve high pressures and high temperature, high noise, and cavitation controls. Cavitations are, we are telling it repeatedly, cavitations will study details after few slides. So, you will find that it is very important for the control valves, you must know it very details. So, they are most suitable for extreme applications which involve high pressure, high temperature, high noise, and cavitations. They can also be differentiated as a single port and double port valve. Already we have seen that there are two types of valves. We can have a double port valves, we have a single port valves. In the single port valves, shut off is tight, whereas in the case of double port valves, shut off is not tight. But in the most of the industrial process, as you know, this never we have a tight shut off, always it is within a range the liquid will flow. Types of sliding stem valve. Single port valve bodies. It has a simple construction and is the most commonly valve body style. We have seen that in the case of 38, whatever the examples we are given, which is a single port valve. They are available in the various types like globe, angle, etc. Right. Generally, single port valves are specified for applications with stringent shut off requirements, because where the shut off is very tight. So, I need this type of valve. You may say that why should I use then butterfly valve? As I told you, the response time of the butterfly valve is very less. That means it is very quick action it will take, whereas in the case of sliding valve, single port valve, even though as it is single, sliding stem, it takes more time. But the shut off, if the shut off is very tight, if you need a very tight shut off, I have to use a single port valve. They use the metal to metal seating surface and they can handle most service requirements. Okay. So, metal to metal surface, that means seat is metal as well as plug is of metals. So, handle most service requirements, that means corrosive requirement, high temperature, all those things can be withstand, though nowadays Teflon can also withstand a high temperature, but not high as obviously the metals like steel. Since high pressure fluid is normally loading the entire area of the port, the unbalanced force created must be considered in selecting actuators for single port control valve bodies. Okay. In the high pressure, if the liquid is coming as high pressure, so quite obviously it will occupy the entire port of the inlet port of the valve, okay, entire area of the inlet port, and the unbalanced force created must be considered in selecting the actuators for single port control valve bodies. The different styles of single port valves and their descriptions are as follows. Single port globe valve, it is the most common form of sliding stem single port valve. It has a linear motion. It has a globe shaped body. Okay. It is shaped, the inside shape of the body, valve is a globe shaped, that is the reason we are calling it globe. They are widely used in process control applications, particularly in the sizes of 2.5 centimeter to 10 centimeter. Okay. That means 1 inch to 4 inch size you will get, because you see that we are converting in SI units or in a CGS unit, but most of the valve, valve, the details you will find like the Fishers and all those who are making the control valves in over the years, you will find they are giving the specification in inches. Since these are American valves, so usually made by the American manufacturer, they still considered in those APS system, but still we are telling it in the CGS or SI units. A typical single port globe valve is shown in figure 1. You can see here the single port globe valve. Okay. You can see here it is inlet body, inlet it is coming here. Okay. Here is a seat, so here is a seat. So, if the seat closes, the liquid cannot flow. This is the stem of the valve. Okay. There is a spring, you can see. There is a here you see, here you can see here, that is there is a packing. So, spring is there. So, diaphragm is not shown here, right. This is a typical single port globe valve. Single port angle valve. Angle valves are nearly always a single port. So, you will see that it is in angle, the liquids are, it is like an elbow. Let us see. They are commonly used in boiler feed water and heater drain service, and in piping schemes where proper utilization of space is very important, because not always we can use a linear, just a linear pipe. When I need a bending, so that time we can use a single port angle valve. They can also serve as an elbow. It is working as an elbow. So, instead of using an elbow, I can use angle valve, which will make the flow control as well as it will make the it will save an additional elbow in the process pipeline. The valve shown has cage style construction. Changes like expanding outlet connections, restricting trim, etc., can be done to reduce the erosion damage. The erosion is a common problem you will find in the control valves. You will see the cavitations. If the cavitation is there, obviously the erosion will be there. This is the single port angle valve. You can see here. Okay, it is inlet port and this is outlet port. Okay, this is a stem of the control valve. You can see here. This is a stem, and this we have the spring here. Okay, this is the inlet, and this is the seat. This is our plug, and this is the seat. Okay, so if it sit tight, so the liquid cannot flow. So it is like an elbow. So it will save one elbow in the process, right? That means if I need proper utilization, so the space is very important. So I can use this type of angle valve, right? It is single port angle valve. Single port bar stock valve, they are small, range from few centimeter to 7.5 centimeter, and they can be machined from any metallic bar stock material and from some plastic. Okay, from any bar, metal bar, we can machine it, and it's from plastics also we can make it. Their flow capabilities are generally lower than those of the general purpose valve. It is not for the high capacities in as it case of the globe valves, not conventional globe valves, okay, but for the low capacity. These valves are used more often when there are special corrosion considerations in chemical industry. In chemical industry, you see, though we are saying the stainless steel we can use, but stainless steel, machining stainless steel is very difficult, as you know. So, in that type of cases where we need a valve where it will not react with the fluid which is flowing to the pipe, So, because any metals, you know, sometimes some metals reacts with some chemicals. So, that type of cases chemicals are more inert, I mean these plastics are more inert in that sense. So, we can use that this type of valves. A typical bar stock valves you can see here, okay, is shown in figure. This is a bar stock valve, same thing, stem spring is there, and you can see this is the bar. So, we call it bar stock. You see here it is coming through here and it is going through this one, this inlet, this is outlet. Double port valve bodies, double port valve already we have seen in that lesson 38. So, we will now look at details. Dynamic force on the plug is more balanced as flow opens one port and closes at the other. Okay. So, dynamic forces on plug is more balanced as flow opens one port and close the other, right. So, there is two valves. So, obviously, if I in one port liquid will flow, in other port liquid will stop. Reduces dynamic forces acting on the plug might allow choosing a smaller actuator than would be necessary for single port valve body with similar capacity, right. So, I need a lesser powerful actuator, okay, that is the reason single double port valves is preferred. Bodies are generally furnished with large sizes 10 centimeter or larger and more capacities. The capacity is also more for this type of valves. Many double port bodies reverses. So, the valve plug can be installed as a fail close or fail open modes, right. We have seen that the valve can be used as a fail open, yard to open or yard to close. Since double port body is reverse, so I can find the reverse, so that I can use it for fail close or fail open modes. Okay, this is a great advantage of the double port, but which we do not have in the case of single port valve. So, same valve can be used, whereas in the case of single port valve we have seen that we have to make the total, we have to change the total valve itself, which is not necessary in the case of double port valve. We can use it either in a yard to close or yard to open. Figure 4 shows a typical double port valve with a globe style valve body. This is a globe style valve body and is a double port. You see here is a double port valve. Okay. So, it is, you see there is a two ports, okay, and two seats. Liquid can flow through this one or liquid can flow through this one. So, always when it is different position, liquid will flow either through this one or through this one. Okay. So, it is a single port, double port globe style valve body. Rotary valves. Types of rotary valves are ball valves. Ball valves shows a high range of volumetric flow and the low susceptibility to wear by erosion streams, right. This is important. This is also true for the butterfly valve, right. We will see that. Hence, generally used for high pressure drop throttling and on off applications. If we need a high pressure drop, because whenever there is a high pressure, there is a problem of the cavitations will be very severe in the case of high pressure drop, because whenever it is comes to the outlet point, there is a low vapor pressure, pressure, there is a pressure drop and there is a formations of the vapor and it will start to corrode erosion will start at the outlet range. So, the seat and all those things will be damaged. Hence, generally used for the high pressure drop throttling on off applications. However, they have a sluggish response in the first 20% of the ball travel, making them unsuitable for throttling applications. Okay, continuous throttling is not necessary. Either you can stop it on off sort of that type of situations I can use it, but the continuous control of the liquid is not possible because of this inherent problem that they have a sluggish response in the first 20% of the ball travel, that means the stream travel, and making them unsuitable for throttling applications. Figure 5 shows a rotary shaft control valve with a V-notch ball. The V-notch produces an equal percentage flow characteristics. Okay, this V-notch will make a V-notch and equal percentage flow characteristics. These valves have a good rangeability, control and shut off capabilities. Okay, the range is higher, that means it has a wide range, this is very important, and it is a control and shut off capabilities are also high. Okay, these are the advantage of this type of valves, and it is also suitable for the control of the viscous fluids and sluddies containing solids and fiber. This is a very common form of situations you will see in the process industries. That means it will always, not necessarily you will find always water, there is a very viscous liquids may flow, it may contain slurries and other fibers. So, that type of situation globe valve is very important globe, I mean ball type of valves will be important. This is, you see, this is a ball type of valves, rotary shaft control valve with a V-notch balls. Okay. You can see here this is a V-notch ball valve. Now, butterfly valves, you can see this is a very common, this is also not very widely used, but it is used for some particular, I mean industry, because if it is suspended particles to avoid cavitations, all those things, the butterfly is very suitable for that type of situation. They require minimum space or for installation and are very economical, particularly because you see since it is a butterfly, so you will have only a valve motor. So, we do not have a stem sort of thing, okay. Only the butterfly, I mean there is a disc sort of thing which will rotate. If it rotates, it will allow the liquid to flow, otherwise it will stop, right. That is a butter, and are very economical, particularly in large sizes and flow capacity or range. So, if you need a large range, that is a great advantage. That means it has usually typically butterfly valves comes with a large range, which is not possible in the case of typical globe valves. We need, if you want to large, then the size of the valve will be enormously big, because in the valve there is a restriction, the stem size, your the plug size and the seat size actually will control the range of the valve also, right. So, those type of restriction, there is no as such seat or plug in the case of butterfly valve. That is a great advantage, that obviously will lead to the higher range of the control valve. They provide high capacity with low pressure loss across the valves. Okay, they provide high capacity with low pressure loss across the valves. In case where operating torques can be very high, butterfly valves may require large actuator. That is another problem. So, if we need a you need a large torque, we need a large actuators, okay, because they have to rotate, right. We will see that how it works. We will show the butterfly valve. So, that I need a large actuators, otherwise it is a very good valve. Butterfly valves are used in nuclear power plant applications with very stringent leakage requirements. Okay. It is applied because in we have a very, I mean, with time constants of the valve should be, I mean, very small. That means it should be immediately shut off, immediately start to flow, that type of situation. But the problem is, if you can want to make complete shut off, butterfly valve is very difficult, okay, because there is no such plug and seat. So, there is always some leakage, but nowadays with some special applications we can make the leakage almost 0. The standard liner can provide good shut off and the erosion protections. Okay. Erosion is not very important here, it is the good shut off is very important. So, the commonly used liner is nitrile or PTFE, which is polytetrafluoroethylene or Teflon. Okay. This can be used as a liner, and this you can see here, this is actually a butterfly valve, right. So, this is a pneumatic signal you can see. Okay. You can see here, this is actually it will rotate and this will rotate, and it looks like this one there. So, that means I have a valve. So, pipe is there, it will look like this one, right. Either it will come to this position or it will completely shut off like this one, okay, or if it goes like this one, there is no shut off at all, right. So, that means you have to rotate it, you have to rotate this one to this one. That means, if the pipe is there, so if I rotate like this one, there is a total shut off, clear. So, it will rotate like this one, okay, it will rotate like this one. Eccentric control valves. Eccentric plug have features of both the sliding stem and rotary valves. Okay, there is a features of the rotary valves as well as sliding stem valves, but unlike rotary valves, it utilizes a massive rigid seat design. Seat design should be very rigid here. So, let us look at many good aspects of both rotary and stem are combined in eccentric valve, right. So, both the combinations are there. So, obviously, in some application this is very stringent. There are basically two types of eccentric control valves. Eccentric disc control valves, bodies offer effective throttling control, they provide linear flow characteristics, okay. An eccentric mounting of disc pulls it away from seal after it begins to open, minimizing the seal wear. So, that is a great advantage, because seal is always, okay, wear. They use standard pneumatic diaphragm or piston rotary actuators. I think this will be seat wear. They are intended for general service application not requiring precision throttling control. Okay. Precision throttling control is not possible, it does not matter. So, this is our eccentric disc control valve. You see here, eccentric plug control valve. Valve assembly combats erosion, and the rugged body and the trim design handle the temperature as high as 400 degree centigrade, and shutoff pressure drops to 10,000 kilopascals, extremely high pressures we can see here. And path of the eccentric plug minimizes the contact with the seat ring when the opening, and reducing the seat wear and friction and the prolonging its life. Forward or reverse flow and the tight shutoff in either direction is possible. Okay. Forward or reverse flow and tight shutoff in either direction is possible. Okay. So, this is a great advantage, though it is very uncommon in any process. Okay. Eccentric plug control valve, you can see here. Control valve selection. General criteria for selection of control valves are the pressure rating, this is most important. Body pressure ratings are considered according to the ANSI pressure classes. The ANSI pressure classes for steel are 150, 300 and 600. The maximum pressure rating is inversely proportional with the temperature. The required pressure ratings are dictated by the application. Flow capacity or the range of the range of the valve, that is also important. On the basis of the flow capacity, we can roughly categorize the selection as follows. Sliding stem valves are used for lower ranges 1.25 centimeter to 7.5, I am sorry, this will be in centimeter. This will be centimeter, right. Ball valves in intermediate capacities, it is coming on 10 centimeter and to 15 centimeter. Butterfly valves for very large sizes 20 centimeter and above. Special consideration like high noise application, cavitation etc. require valves designed with the special trims. Okay. Trims, as I told you, it is an entire assembly we are calling about the trims. Flow characteristics. A complete dynamic analysis is required for determining the proper flow characteristics desired. What are the typical flow characteristics I need? Equal percentage, linear, quick opening, these are basically flow characteristics. However, there are certain general guidelines which hold true, but there are few exceptions. You see, we are saying that the constant delta P, this is a table, the selection based on the flow characteristics, selection of the control valve pressure drop, that is a pressure drop across the control valve, inherent characteristics, constant delta P, linear, decreasing delta P with increasing load, linear, we will use linear control valve, delta P at a maximum load, decreasing delta P with increasing load equal percentage, increasing delta P with increasing load, delta P at maximum load 200% of the minimum load, the linear, increasing delta P with increasing load, it is quick opening. Rangeability, it is the ratio of its maximum and minimum control flow rates. It is the ratio of the maximum and minimum control rates, right. We have seen this thing in the while we are doing the analysis of the equal percentage valves in the lesson 38. Exceptionally wide ranges may be required to handle wide load swings or combination of startup, normal and maximum working condition. But usually rangeability is not very important. We have actually the variations of the flow capacities is not that wide in any process. Rangeability is obviously there, it depends on what type of fluid is flowing. So, you may have a very high range, you may have a small range, but the variations of the flow capacity is not very common in any process. In general, rotary valves have greater rangeability than the sliding stem valves, right, quite obvious. Temperature limits. The thermal considerations include the strength or ductility of the body material as well as the relative thermal expansion of the valve internal parts. Okay. Now, this it does not matter much if I use a you metal like a steel and all those things, this ductility, all these things will not matter much. But sometimes it if the liquid temperature is extremely high, I mean this is, you should consider this thing also, what type of material is to be used to make the seat, to make the plug and all those things, to the inlet, I mean through the which the liquid is flowing, there is all these things to be considered. Temperature limits may also be imposed due to disintegration of the soft parts like seat rings, seal, piston, etc., which are made of various elastomers, plastics, etc., at high temperatures, or loss of resiliency at low temperatures. Okay. This is also important. Shut off leakage, this is very, we should consider. Tight shut off is very necessary in case of high pressure valves, okay, because leakage can cause seat damage, right. So, the tight shut off is necessary in case of high pressure. When the pressure is high, obviously if the shut off is not tight, there will always leakage. So, since leakage can cause a seat damage. At the same time, however, we must consider, we should not over specify the shut off leakage. In some application may unnecessarily increase the cost, right. Pressure drop, this is another important thing, pressure drop across the valve. Sliding stem valves can tolerate more pressure drop than the rotary valve. Okay. Sliding stem valves can tolerate more pressure drop than the rotary valves. Noise and cavitation, both of which are accompanied by high pressure drop, must also be considered while selection, right. End connection requirement, this is another important thing. End connection desired are important consideration, because sometimes the desired connection style is not available and the valve style being considered. Okay. This is another important thing, what type of pipe you are installing, that type of, and what is the end connection, that means inlet connection and the outlet connection to the pipe is to be considered also. Not always all the valves you have the same, all types of end connections you can make it. Accordingly, you have to choose the valve. This is a choice of valves obviously. If piping specifications calls for welded connection only, the choice is limited to the sliding stem valves, okay. Welded connections only, since rotary valves available are expensive there, right. Material selection, generally materials like carbon steel, alloy steel, stainless steel, which have a better strength, pressure and retaining and corrosive properties are used. Okay. Stainless steel, I earlier also told you, it is not very easy to machine stainless steel. I mean alloy steel, carbon steel, okay. Obviously, the stainless steel is also low carbon steel basically. The life cycle cost, this not only includes the initial cost, but also the maintenance cost of the, because control valve is to be maintained very regularly. Usually all control valves will be bypassed by a globe valves always, because during the routine maintenance you plan 24 hours and when the plant is running, you cannot shut off the plant. So, that the globe, that actual control valve is removed and we will put a globe valve there. Cavitation, we have talked about the cavitation so much. What is this cavitation? Let us look at very detailed, because this is very important. You must stop the cavitation, otherwise the erosion will start and the valve will be entire calibrations you have to, whatever the typical flow characteristics you have desired, you may not get this thing, ultimately leading the poor product quality. So, those things are very important. So, cavitation, you must study the cavitation details, and we have to stop the cavitations inside the valve. At the fundamental level, cavitation is nothing but the growth and collapse of the cavities in a liquid. Okay, growth and collapse of a cavities in a liquid. These growth and collapses result from the fluid pressure dynamics, as I told you, from high pressure to low pressure. Okay. In case of control valves, a bubble is formed when the local pressure of the liquid drops to the vapor pressure. Okay. When the bubble will be formed, that means when a local pressure of the liquid drops to the vapor pressure, because at the outlet of the valve, or just when it crosses the seat or the seat of the valve, then the pressure will drop there. Okay. So, if the pressure drops, obviously the bubble will be formed, and it collapses when the local pressure, because as it proceeds through the pipe, it will collapse. So, it will collapse when the local pressure, because the pressure will be recovered once you proceed through the outlet. The pressure drop, pressure loss will be recovered, as it happens in the case of orifice and venturi, same thing here also. Then that bubbles will collapse again, because pressure is increased, the bubble will collapse. Clear? Rises above the vapor pressure. Now, this rise of bubble and its consequent collapse leads to the formation of cavity. Okay? That means the formation of the bubble, rise of bubble, and its collapse will lead to the formation of cavity. Consider the mean pressure profile shown in figure 9. In next figure we will see. The shape of this general curve is a consequence of the pressure changes resulting from the velocity changes and the available energy dissipation. Okay. There is energy dissipation inside the pipe, and the shape of the general curve is a consequence of pressure changes, velocity changes in the dissipation. This you can see mean pressure profile of a control valve. Okay. You see here pressure is here, then now pressure is, there is a large pressure drop and it will increase little bit. At the outlet it will come to the P2, but inside there is a large pressure drop. So, the cavitation will start here when the pressure drop is high, okay, when the pressure difference is high. So, the cavitation will start here. Okay. This is P1 minus Pc, this is the minimum pressures here. Okay. So, you can see there is a large pressure drop. So, the cavitation will start here, right. So, this is the flow direction, that means I am proceeding from the inlet to the outlet of the valve. This is inlet, this out to the outlet of the valve, clear. Now, the mean fluid pressure decreases from the inlet valve to some minimum value and recovers partially at outlet. That is I told you, like orifice, it is the same thing, it is a restriction, is not it. Valve is very similar to restrictions. We have seen the orifice, venturi, all these things, we have a restriction there, right. We have seen in the case of venturi, the restriction is, I mean the valve pressure recovery is better, pressure drop is not that high. Here you see the pressure will be, they will fall, is a restriction, again it will be recovered to some extent. This means the fluid pressure decreases from the inlet valve to some minimum value and recovers partially. This is a minimum value, okay, PV, what we have seen. This is our minimum value PVC. So, this is P1. So, P1 minus PVC is this much. This is the minimum value of the control, where is the pressure. Cavitation theoretically occurs when the minimum pressure is equal to the vapor pressure and the outlet pressure is above the vapor pressure. Okay. Now, where it actually happens? You see this, it is what I am saying, cavitation theoretically occurs when the minimum pressure is equal to the vapor pressure. When it happens? It actually will happen when the liquid coming in through the inlet point, it is going through the plug, going to the seat, okay, through the plug will, I mean, make the control, and to the outlet. So, the cavitation will start where? Cavitation will start just when it will leave the seat of the valve, clear. Just when it will leave the seat of the valve, the cavitation will start, because as it proceeds to the outlet. So, that is the portions actually when the cavitation will occur. Cavitation theoretically occurs when the minimum pressure is equal to the vapor pressure. Okay. Minimum pressure is equal to the vapor pressure, very common in the case of, it is very common in the case of LPG industries, where the vapor pressure is little less. Okay. So, whenever this pressure falls, then obviously cavitation will start, and the outlet pressure is above the pressure. When the above the pressure, vapor pressure, then what will happen? Outlet pressure, because pressure will be recovered, that time that bubbles will be collapsed. Okay. So, the cavitation will start. How to overcome the cavitation? So, cavitation is there, you must, I mean, check how to overcome the cavitation. Material selection. It is sometimes possible to create a cavitation tolerant environment by selecting materials more resistant to the cavitation attack. Okay, we have to shape the inside the valve so that it will more resistance to the cavitation, that is number 1. Number 2, introducing resistance in flow path. Due to this, the overall fluid pressure recovery is reduced. Obviously, the pressure drop will be, there is a pressure loss obviously. So, this pressure loss actually will lead to the more pumping cost obviously, okay, but we can avoid the cavitation. Okay. Introducing resistance in the flow path, and due to this, the overall fluid pressure recovery is reduced, thus avoiding to go above the vapor pressure. Even it does not stop cavitation altogether, it certainly reduces the intensity. Okay. Intensity of the cavitation will be reduced. Now, accessories of the control valve, there are accessories I talked about at the initial stage. So, let us discuss little bit accessories. There are many accessories associated with the control valves like valve positioners, limit switches, solenoid valve manifold, supply pressure regulator, fail safe systems, pneumatic lockup system, etc. But most of important of all these things are the valve positioners. These accessories help the control valve function better with more accuracy and also act as a safety precaution. This is also, safety is very important, as a safety precautions also will be used. Out of all these valve positioners are the most important, out of all these valve positioners are the most important accessories. So, we will study the valve positioners in details. Clear? Now, valve positioners. What is this valve positioners? You see that it, as the name implies, actually it will position the stem, position the seat, position the plug on the seat of the valve more precisely, much better way, right, so that there is no hysteresis. The valve positioners is necessary due to the hysteresis. We will first look at the what is the control valve hysteresis, we will look at that. Need of the valve positioners. Valve hysteresis, this is more, see the friction in the packing, because we need a packing. Why? Because you see the inlet pressure, inlet liquid is coming inside the valve, which is might be globe in shape or whatever it may be, through the seat it is, and the plug, space in between the seat and the plug, liquid is flowing to the outlet line, but this plug actually connected to the stem. So, the plug must, this entire globe should be separated from the other part of the control valve, from the bonnet and all these things. Okay. So, what will happen? We need some packing. So, packing will prevent the liquid flowing out. Okay. There is only one path of the inlet and one path of the outlet. If there is improper packing, then what will happen? Liquid will flow through the packing region. That is not allowed because the high pressure liquid. So, I must have a very good packing. So, the packing, the problem is the packing will introduce a frictions. Okay. So, that will make the hysteresis of the control valve. The friction in the packing and the guiding surface of a control valve causes a control valve to exhibit hysteresis as shown in figure 10. The stem position increases along the lower curve as pressure is increased. Okay, let us look at, you see, I have signaled to the control valve, okay, PV, and this is stem position, okay, or lift, what do we call it, sometimes we call it lift, y axis I am placing lift and x axis the control signals, okay, pneumatic control signals. I am giving the control signals, but I am not getting any stem position. Suddenly there is a stem position, it is increasing, I am changing the signal, now it is not, now when it is friction, overcome the friction, it is going like this. While I reducing, you see, while I reducing the, this signal to valve, because x axis is signal to valve, while reducing the signal, pneumatic signal, the stem position is not coming down. It will remain for some time the same position, after that it will go. So, this is H is the hysteresis of the control valve. To kill this hysteresis, I need a valve positioner. Let us look at, it decreases along the upper curve as pressure is decreased. Okay, we have seen. As the moment air pressure signal reverses, the stem position stays in the last position until the dead band H is exceeded. Okay, this H is exceeded until unless I cross the H is the dead band of the pneumatic signal. After that, it will start to react, right, both in the, when it is going, the stem is moving up and moving down. Might be this H is small, whatever we have shown that to, to understand, so that you will understand nicely, but it usually is quite small, even if you do not use valve positioner. After this, the pressure increases or decreases along the path shown by the arrows. Okay, we have seen. Okay, pressure is increases, stem position changes, this is the pressure. If the valve is subjected to slow periodic variations in pressure, a typical path taken by the stem will be PQRS. Okay, if I now give a slightly cyclic variations of the pneumatic signal PV, we will find that there is a typical path taken by the stem will be PQRS. Clear? What is PQRS? You can see the hysteresis curve. Clear? Now, effects of the valve hysteresis. What is the effect of this hysteresis? Let us look at. Hysteresis is a nonlinear phenomena and cannot be expressed by transfer function. The presence of hysteresis in the valve can cause the control signal to oscillate or exhibit a limit cycle. Okay, it is show a oscillate or limit cycle. This limit cycle contributes to the wear of the valve, that means valve will be damaged very quickly. Now, how to eliminate the hysteresis, valve hysteresis? Let us look at. Hysteresis being a nonlinear phenomena cannot be removed or reduced using controller tuning. Controller tuning will not do, it is a nonlinear phenomena. What we can do, The only way to reduce the effect of the hysteresis is through the use of the valve positioner. We can valve positioners we will see is another control loop, which is with a proportional control, which will position the valve precisely at the position where we need. This is the main reasons of using valve positioner. Okay, this is to kill the hysteresis. Let us look at about the valve positioners. Valve positioners is nothing but a high gain proportional controller, receive a set point signal from the primary controller and a measurement from the valve stem position. Okay. I am getting a set point signal from the main controller and I have a stem position. If there is an error, it will make some control, it will make proportional control signal. Okay, we will go to the diaphragm of the control valve. So, by this I can get a precise, so that now the stem position also is to be measured. This is most important. Previously we have seen that we are not measuring the stem position, but if I install the valve position is the integrated part of a valve body. It is actually rigid to the valve body, but I need a, if I need a valve positioner, then what will happen? Obviously I need a, I have to measure the position of the stem. Okay. If the actual position which is coming from the control signal or controller does not match with the position which is showing by the valve stem positioner position sensor, so obviously I have to take some action. I have to move up and down until unless this position exactly matches with the corresponds to the control signal which is coming from the controller. Let us look at this. The addition of the valve positioner to control valve introduces a form of cascade control. It is basically a cascade control. We have seen the cascade control, 2 loops, okay, in nature. So, we have seen the cascade control is extensively used in process, thus increases accuracy and also speeds up the response of the valve. Okay. So, the addition of the valve positioner to control the valve introduces a form of cascade control and thus increases accuracy and also the speeds of the response of the control valve. So, the control valve response also will be increased by this position. This is very important. Okay. That is the reason people are using valve positioner. Okay. Most of the control valves, especially if the valve is large in size, we need a control. Okay. The only pneumatic signals may not be sufficient to, so I need a valve positioner there, right. A typical control valve with a positioner is shown in figure 11. You can see here. You see this is our a control valve. Control valve already you have seen in many situations, okay, but we have not seen the valve positioner. This is the valve positioners with the control valve. You see what will happen. You see here. So, this is our valve, typical valve body, and the liquid is coming in through this, flowing through this one, it is going to the outlet, fine. This is the stem, this is the our plug and this is our seat, this is the seat and this is a spring, and you see here is a packing, okay. This packing should be very tight in the case of control valve, otherwise there is a problem, because if there is a packing, then why I am saying repeatedly about the packing, you see what will happen if the pressure of the liquid is high, so it will go through this one, so that is not allowed. So, this packing should be very tight, right. Now, if I use a tight packing, there is a larger frictions of the stem, because stems will move, only the stem of this control valve will move, nothing else, the stem will move, okay. The spring will squeeze if it goes up, okay. Now, when the pneumatic signal remove this, it will go down, right, clear. Now, what will happen, you see, if I now, sorry, it will, if the pneumatic signal is removed, actually the valve will go up. So, it is here to close. If we give the pneumatic signal, this is a diaphragm, so diaphragm will give the pressures, it will go like, it will squeeze and it will come, otherwise what will happen, it will go like this one. Now, what will happen, you see here, there is a valve positioner. So, there is a friction. Now, the valve positioners is a device, it is a cascade control. So, I am getting a signal, pneumatic signals of PC from the controllers, that is 3 to 15 psi of signals I am getting, it is coming to the, now I am measuring the valve positions also through this one, stem position, the stem positions I am measuring. So, what will happen, it is getting signal and it is also this, if it does not matches, then what will happen, if it does not matches, it will produce some control signal. It will produce some control signal and this process will continue until unless this valve position, whatever it is showing on the indicator or measurement system, will exactly matches with the signal control signal PC. PC is basically corresponds to some valve position, stem position, right. So, this way, so the control loops, I mean this way I can use a output of the controller will come here. So, this way I can make the valve positions and make the systems very sturdy. I mean I can make the system so that it will work, I mean without any error in the stem position. This is very common because if it is a large friction, so obviously what will happen that there will be some mismatch of the position, but that can be I mean recovered, and that can be exactly valve can be positioned, valve stems can be precisely controlled by using the valve positioners, right. So, this is all about I am talk about this I mean valve positions and all these things. You see here these arms attached to the stem to sense the valve position, and this is arms which is sense the stem of the valve position, because this will go to parallel, and this is the valve position, signal from the PC will come, right. And as shown in figure 11, a typical valve positioners has the following features. What are the features of the valve positioners? Let us look at a set point that calls for a desired stem position from the primary controller PC, okay, it is coming from the primary controller. A measurement in the form of stem position x, okay. So, these two will be I mean these two will be compared, this PC will be compared with S, obviously PC will be compared with X in a valve position. Accordingly, it will generate a control signal PV, which will go to the diaphragm of the control valve, okay. A pneumatic output in the form of a pressure to the valve top PV will go, okay. This will actually give the proper position of the control valve. So, this is all about the positioners of the control valves, and the control valves I mean, and most of the you see the most of the figures actually we have taken from the Fisher's control. They are the largest manufacturer of the control valves. This is available in the website, so there is no problem. If those who want to look at the details of the figures, they can go to the particular site and look at those figures, right. And with this I come to the end of the lesson 39 of the industrial instrumentation.